Today, we're tackling a problem that, kind of runs the modern world from behind the scenes. How do you find the absolute best way to match tasks to resources?
All right, so here's what we've got on tap. We're going to start with the basics. What's the matching game all about? Then we'll get into the secret sauce, this really cool idea called the power of zero. From there, we'll look at what happens when things get messy, impossible assignments. Then we'll meet the assignment problem's famous, much tougher cousin, the traveling salesperson. And finally, we'll wrap it all up by seeing how this stuff actually affects our world.
All right, first up, the ultimate matching game. So, what exactly is the core challenge here? Let's get right into it.
Okay, so picture this. You've got, say, 4 jobs that need to get done, and you've got 4 different machines. The thing is, not all machines are created equal for every job, right? Machine 1 might be super fast at job A, but terrible at job B. So every single combination, every possible match, has a different cost attached to it. The big question is, what's the cheapest way to get all the work done?
And this is what that looks like when you map it out. It's called the cost matrix. See all those numbers? Each one of the cost of pairing one specific machine with one specific job. Our mission, should we choose to accept it, is to pick one assignment for each row and column so that the grand total cost is as low as it can possibly be. So formally, this is what's known as an assignment problem. And the number one rule, the one you absolutely can't break, is that it has to be a one-to-one match. Each machine gets exactly one job. No more, no less.
Okay, so how on earth do you solve this thing? I mean, you could try every single possible combination, but that would take forever. Well, lucky for us, there's a much more elegant way. It's called the Hungarian method, and it's all about harnessing the power of zero.
This is where things get really clever. The Hungarian method doesn't just look at the raw cost numbers. Instead, it flips the script and makes us look at opportunity costs. Think of it like this. It's trying to find the assignments that are such a good deal, they're basically free compared to the other options. They become the no-brainer choice for that row or column.
So how does it work? Well, it's a really neat 3-step dance. Step 1, we find these zero-cost options by doing a little subtraction magic on each row. Step 2, we do the exact same thing for the columns, which uncovers even more of these golden opportunities. And then for the finale, step 3, we just assign our tasks to those zeros. It's a beautiful way to find the perfect solution without having to do a million calculations.
Right, but let's be real. The real world is messy, isn't it? It's never a perfect little square. So what happens when you have more jobs than machines? Or what if a certain pairing is just forbidden?
Let's take a look at an unbalanced problem first. So here, we've got 4 machines, but 5 different areas to place them in. See how the grid isn't a perfect square anymore? That's a problem. Our nifty Hungarian method won't work, at least not yet. But the solution is actually pretty clever and simple. We just add a dummy machine. It's totally fake, a placeholder row with all zero costs. Boom! The matrix is square again. And whatever area ends up getting matched with our dummy machine, well, that's just the area that's left empty. Problem solved.
Okay, now for a different kind of headache. What if there is a restriction? Let's say machine 2 physically can't be put in area C. Maybe it doesn't fit, or there's no power outlet. Whatever the reason, it's a no-go.
How do we handle that? Easy. We just assign a ridiculously high cost to that one spot. We're talking an infinitely high cost, often just written as a big M. It's basically telling the algorithm, hey, whatever you do, do not pick this one. And because the algorithm is trying to find the lowest cost, it will avoid that M like the plague, guaranteeing that impossible match never makes it into the final answer.
So, just to quickly recap those 2 clever workarounds, if your problem is unbalanced, you add a dummy row or column filled with zeros, and if a pairing is impossible, you slap a huge cost on it to scare the algorithm away. Simple, right?
All right, now that we've got the basics down, let's level up. We're going to talk about a famous and, frankly, much harder version of this puzzle. It's called the traveling salesperson problem, or TSP for short.
Now, with the TSP, the goal is totally different. It's not just about matching one thing to another. It's about finding the absolute shortest path, the perfect order of visits that hits every single city on a list exactly once before returning to the start.
And this isn't some newfangled problem either. It has a pretty cool history. It started out as a thought experiment for mathematicians back in the 20s and 30s, but by the 1950s, it had become a super critical tool for things like military logistics. Talk about a glow-up.
And the reason the TSP is so legendary, it's just mind-bendingly complex.
The number of possible routes doesn't just grow, it explodes. For just 10 little cities, you're looking at over 180,000 different routes. Trying to check them all by hand? Forget about it. It's literally impossible.
But here's the crazy part. Even though it's so hard to solve, we use it everywhere. Seriously, it's logic that plans school bus routes, tells a robot how to drill holes in a circuit board in the fastest order, and of course, it's what optimizes the delivery routes for everything from your pizza to your packages.
Okay, so let's tie all of this together. Why should you care about any of this? What's the point? What does it all mean for us?
You know, the really crucial thing to remember here is that in our world, a world with limited time, money, and resources, just finding a solution isn't enough, not even close. The goal is always to find the optimal solution, the best one, the cheapest, the fastest, the most efficient way to get things done. And this kind of optimization, it's happening all around us, all the time, completely hidden from view. It's the silent engine that makes so much of our modern lives work. So think about it. From the route your GPS just calculated to the way your online shopping gets to your door, how many of these invisible assignment problems are being solved for you right now? It's a fun question to ponder. Thanks for watching.